3.3 is an introduction to probability, and it starts with a couple of terms. Experiment is an activity or occurrence with an observable result. Rolling a die might be your experiment, okay? Doing something, that's your experiment. A trial is each time you do that task. If I roll a die 50 times, then there would be 50 trials, but the experiment was rolling a die. Outcomes are the possible results, and sample space is the set of all possible outcomes for an experiment. So sample space is the first term that people really struggle with. It's just what could possibly happen. List out everything that could possibly happen. Example one, we've got a spinner. So you've probably played board games or you flick that little arrow and it spins around and gives you a number or whatever. But in this problem, it says give the sample space. We're going to call sample space S, and it's going to be a set. So put little squiggle brackets, but sample space is just what could you possibly get. And so in this case, you flick that arrow, you're going to either get a 1 or a 2 or a 3. That's the sample space. And that's all there is to it, seriously. Part B, students are classified as in grade 9, 10, 11, or 12, and also as male or female. So list out the sample space. So this one's a little bit harder because there's more to it, but you could be 9 male, 9 female, 10 male, 10 female, 11 male, 11 female, 12 male, 12 female. Sample space. And then the next question is going to talk about how many items are there in the sample space. So it's important to know, we can just count that. Looks like there's 8 items in the sample space. That's going to be important for some of the later questions. Part C, the number of boys in families with exactly 3 children. So number of boys. Well, if there's 3 children, then you could have 0 boys or 1 boy or 2 boys or 3 boys. That's it. That's the sample space. What is possible in this specific scenario? All right. The next one, the vowels in the English alphabet. I don't count Y as a vowel. I know, and sometimes Y, but we're talking about the vowels in the English alphabet, typically A, E, I, O, and U. That would be the sample space for that experiment. More terms. Event is a subset of a sample space. So it gets kind of tough because people didn't learn what a subset was in the last lesson. All right, a subset. Simple event is an event with only one outcome. Certain event is an event that equals the sample space. Impossible event, an event that equals the empty set. Mutually exclusive events, or events that cannot occur at the same time. All right. So let's talk about a subset real quick. I like to think about a subset as just any possible combination of things. So if your sample space is 0, 1, and 2, all right? So remember when we talked about subsets in the last lesson, the number of subsets is going to be 2 to the 3rd power in this case. If there are 1, 2, 3 items in the sample space, then there must be 8 subsets. And I think of subsets as like a Christmas list. If that's my Christmas list, then what could you possibly buy me for Christmas? Well, maybe you buy me nothing. Or maybe you just give me a 0, or just a 1, or just a 2. Or maybe you give me a 0 and a 1, or a 0 and a 2, or a 1 and a 2. Or maybe you get me everything on my list like that. I see 8 different items. That's 8 different subsets of that sample space. So when we're talking about an event there, an event is just one of those subsets. So let's say our event is that you get me a 1 and a 2. That is one of those subsets of the sample space. So that's something that students struggle with kind of a lot. So mutually exclusive, when we drew that as a Venn diagram, mutually exclusive means there's no overlap. And mutually exclusive as a Venn diagram looks something like this. There is nothing in the overlap. The overlap is the empty set. So number 2, write each set. A, bless you, says there's an experiment where an ordinary 6-sided die is rolled. So we already talked about the sample space for a 6-sided die. Sample space is just what could you possibly get. Could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. E, the die shows an even number. Okay, so E is the event that the die shows an even number. So we're just gonna list out the even numbers here. All right. So the even numbers 2, 4, and 6. That is one of the subsets of that sample space. Now, how many subsets are there? Remember, how many subsets there are? There'd be 2 to the 6th power, whatever that is. What is that, 64? There are 64 different subsets. I just listed one of them. 246 is one of those 64 subsets. Event G, the die shows a number greater than 5. A number greater than 5, well, that's just this. And that's it. There's not a lot to it. Part B, they give you the sample space. H is the event. The family has exactly 2 girls. Okay, so B must be boy and G must be girl. So exactly 2 girls. We're looking at what, this one and this one and this one. So H is that event containing those 3. BGG, GBG, and GGB. K, the 3 children are the same sex. So that's either going to be BBB or GGG. J, the family has 3 girls. So that's just this one. Number 3, a coin is flipped until both a head and a tail appear, or until the coin has been flipped 4 times, whichever comes first. The sample space is this. So I think this is a tough problem. If I didn't give you the sample space, you'd have to figure it out using a tree diagram. And so think about what happens. A coin is flipped, so either it's heads or tails. And so this says a coin is flipped until both a head and a tail appear, or until the coin has been flipped 4 times. So let's say the first time it flipped was a heads. So we flip it again, heads and tails. So this would be the end. That would be the end of that branch of the tree because both a head and a tail have appeared. But if I go H and then a second H, I'd have to flip a 3rd time. And this one would be the end of the line because both a head and a tail have appeared. And if it was HHH, I'd have to flip the coin a 4th time, at which point, either way, that's the end of the line because you flipped it 4 times or you flipped both a head and a tail. So let's say you take the bottom branch. If you flip the first one and it was a T, then you flip again and it's either heads or tails. And if it's tails heads, that means you've shown both head and a tail. If it's tails tails, you flip again a 3rd time. If it's tails tails heads, you've seen both results. If it's tails tails tails, you flip again, at which point you've either seen them both or you've flipped 4 times. And so either way, that's done. So HT was this one, and HHT was this one, and HHHT was this one, HHHH was this one, TH was this one, TTH was this one, TTTH was this one, and TTTT. All right, so if they didn't give you the sample space, it's kind of difficult to come up with that tree in this problem because you really, really have to think about what it's saying. But regardless, we have the sample space, so we should be able to come up with any of these events. Write each of the following events in set notation. E, the coin is flipped exactly 3 times. So 3 times, that's this one and this one. And that's it. So E equals H, H, T, 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 H. F, the coin is flipped at least 3 times. Well, at least 3 times, it's going to be this one, this one, this one, this one, this one, this one. I see 6 items. 6 items. So F, H, H, T. Do you think it matters what order those things are written in? Not really. Imagine putting them in a box, shake up the box, mix them all up. It doesn't really matter as long as you've got those 6 items. G, event G, the coin is flipped at least 2 times. At least 2 times is going to be everything, right? So I could write out everything, but there might be an easier way of doing this. Instead of writing everything, I'm just going to say it equals the sample space. That's the easiest way to do it, or list them all out. H, the coin is flipped fewer than 2 times. Fewer than 2 times. Well, that's nothing, right? That's not going to happen. That's not going to happen. So H equals the empty set. Sometimes you can read the empty set as nothing. Set operations. So again, we've got these symbols, the intersect symbol and the union symbol. It says let E and F be events for a sample space S. I read this as and. E and F occurs when both E and F occur. The union of E and F I will read as or. E or F occurs when E or F or both occur. So notice this or both. All right, one or the other or both of them. That's important because I know sometimes the word or uses the word both and sometimes it doesn't want to use the word both. But in this case, one or the other or both. And then this symbol I read as not E. E complement occurs when E does not occur. So learn those symbols. They come up all the time in the next couple of chapters. Number 4, study of workers earning the minimum wage grouped such workers into various categories, which can be interpreted as events when a worker is selected at random. Consider the following events. All right, E, the worker is under 20. F, the worker is white. G, the worker is female. Describe the following events in words. So what does this mean? Not E. Okay. 20 or over, 20 or older. So we would say something like worker is 20 or older. You got to be really careful with your language because if you say over 20, then what about a 20-year-old? So be really careful, be really precise with your language. So F and not G. F and not G. So we could say worker is white and not female. Now, there may be a more condensed way of writing that. If you can shorten the language a little bit, then feel free. But the way that literally says the worker is white and not a female. Okay, did I do that right? Does that seem good to you? Okay, last one, E or G. I would say worker is under 20 or female. Raise your hand if you're under 20. Okay, put it down. Raise your hand if you're female. Okay. Raise your hand if you would be in that set of E or G. Shouldn't everyone in here be raising their hand? Everyone in here is either under 20 or female. Everyone that is except for, there's one person in here that wouldn't have their hand up. Me, right? As far as you know. All right, let's move on. Okay. Something missing? Do you have an example 5 there that's missing? Where did... It's at the bottom of the last slide. Ah. Thank you. Example 5. Let S equal 1, 2, 3, 4, 5, 6, the sample space for tossing a single die. Let E equal 4, 5, 6, and G equal 1 and 2. Draw a Venn diagram showing that E and G are mutually exclusive events. Okay. So E is the set 4, 5, and 6. I guess we don't need commas there. We can just do a 4 and a 5 and a 6. G would be the set 1 and 2. And this box is the universe, and the universe includes everything. There's nothing outside of that box, but there is something inside that box, but not inside the circles. What's the only other number I haven't put on there yet? 3. Picture's going to look something like that. There's no overlap, okay? There is no overlap. That's a picture of E and G equals the empty set. Mutually exclusive events. Now, we get into probability, and this is basic probability. And people get super confused by the notation because they're not comfortable with this notation. But all that in means is how many? The number of things there are, all right? So I want you to go back to the first time you started learning about probability. Simple probability was just part over total. Save yourself a lot of headaches and a lot of hassle by understanding that definition right there. When we talk about probability, it'll get complicated in the next chapter or two. It will get complicated, but you can always boil it down to this. Probability is part over total. The end. Whatever else happens, got to go back to part over total. The probability of an event is always going to be a number between 0 and 1. Might be fractions like 1/2, or it might be a decimal like 0.75. But when you're talking about probability, it has to be between 0 and 1. Number 6. Suppose a single fair die is rolled. Use the sample space S and give the probability of each event. E, the die shows an even number. Okay, all you have to do is how many over how many. That's it. So the probability of event E, according to the definition that was given above, is the number of items in E divided by the number of items in the sample space. That's the formal equation. But really, all you have to do is say, well, E, even number is 2, 4, and 6, right? So this is literally just going to be 3 of those over 6 in the sample space. It's 1/2. You can say 1/2, you can say 0.5, it doesn't really matter, but that's the probability. So then part B says the die shows a number less than 10. Less than 10, so probability of event F equals the number of items in set F divided by the number of items in the sample space. But F, let's think about numbers less than 10. Well, when I roll a die, it's 1, 2, 3, 4, 5, 6. All of those are less than 10, right? All of them. And so my fraction is going to be 6 items in the event divided by the 6 items in the sample space. That reduces to 1. That's like a 100% chance, right? A probability of 1 is the same thing as a 100% chance. That's a certain event. Earlier, we talked about a certain event. That's definitely going to happen. What's the probability that I roll a number that's less than 10? Well, 100%, right? And that's a probability of 1. Next one, the die shows an 8. Well, you can't do that. That's an empty set. You're not going to roll an 8 on a die. So probability of event G equals the number of items in event G divided by the number of items in the sample space. Well, that's 0 out of 6, or 0. That's an impossible event. Impossible. Now, the hardest questions that you're going to get, it's not my fault, it happens in all probability classes, are when they talk about a deck of cards. And it's hard for some people, especially people that don't play cards and don't know what kind of cards are in a deck of cards. So I put this on here just to kind of show you what kind of cards are going to be in a deck of cards. There are things that you kind of need to know in order to answer these questions. Like there are 52 cards in a deck. That's a really important number. There are 4 suits, hearts, clubs, diamonds, and spades. There are 4 suits. That's what they're called. Okay. There are 13 cards in each suit. That's another important number. So you got numbers like 4 suits, 13 cards in each suit, 52 total cards. Hearts and diamonds are red, so that means there are 26 red cards, 13 plus 13. And spades and clubs are black. That means there are 26 black cards. There are just things that you need to know about a deck of cards. Each suit has an ace, a king, queen, jack, and cards numbered from 2 to 10. That's good to know. Jack, queen, and king are called face cards. Use your common sense. They literally have faces on them like this king does. An ace is not a face card because it does not have a face on it. Okay, so Jack, queen, and king are face cards. If there are 3 of them in each of the 4 suits, that means there are 12 face cards. Sometimes an ace is a value of 1, and sometimes an ace is the highest value of 14. That doesn't come up nearly as often as some of that other stuff. But if you don't know anything about a deck of cards, you're at a disadvantage. So try and pick that up if you're not familiar with it, because you'll be asked several different types of questions, and it'll get hard. Next chapter is even harder. Number 7. If a single playing card is drawn at random from a standard 52 card deck, find the probability of each event. So part A says we're drawing an ace. So according to the definition that you were given, part over total. Probability is part over total, right? Part over total. I want to know the number of aces over the number in the sample space, or the number in the total deck of cards. So how many aces are there, do you know? There are 4 aces. Out of how many cards are there in the sample space? 52. That number comes up a lot. So 4 out of 52, I don't care if you reduce the fraction. My general rule is if it's easy to reduce the fraction, reduce the fraction. If it's not easy to reduce the fraction, give me a decimal. So 4 over 52, that's 1 over 13. That one's fairly easy. If you gave me the decimal there, no big deal. That's fine. Usually a decimal I would round to 4 places. Okay, drawing a face card. So with the probability of a face, so I want the number of faces. Over the number in the sample space. So go back and look at that picture on the previous slide if you need to, but that's something that it would help if you knew how many faces there were. There's a king and a queen and a jack in each of the 4 suits, right? So 3 cards out of in each of the 4 suits, that's going to be 12. There are 12 face cards out of 52. So again, if you can reduce that fraction, that's maybe good. You know, it reduces to 3/13. If you can't reduce it, use a calculator, give me a decimal approximation. If you leave it as an unreduced fraction, I'm fine with that too. Honestly, if you left that as 12 over 52, I'll probably be okay with that. Drawing a spade. So probability of spade looks kind of like this. It's black. It's one of the black cards. That's what a spade looks like. And so a spade is one of the suits, right? We need to know the number of spades over the number in the sample space. Does anybody know how many spades there are? 13, right? 13 spades, 13 hearts, 13 diamonds, 13 clubs. Out of 52 in the total, that's going to reduce to 1/4. Drawing a spade or a heart. So probability of spade or heart. So the number of spades or hearts over the number in the sample space. Anybody know how many spades or hearts there are? 26, right? Okay. 26 out of 52 reduces to 1/2.